Well, thank you very much. Good morning. And prior to getting into the presentation today, most certainly I'd like to thank a number of people. Co-collaborator Tim Townsend, who I think all of you know very well, has been very helpful on this project, providing a lot of background information. As John indicated, much of my work is around sorbents, do work with water purification, air purification, and here, having Tim's knowledge and experience with landfills and the various issues has been extremely helpful to us getting the project funded and then moving forward with the results. Certainly the students are instrumental in collecting the data and carrying it forward. And I especially need to thank Regina Rodriguez, who's here today in the back, for a number of reasons. One, she has done an outstanding job in mentoring Rachel, who recently completed her master's degree through this project, and then Morgan, who is presently a bachelor's student and looking forward to going on and continuing with a Ph.D. Now, I moved to Florida in 2000, and here's why I also need to thank Regina. We talked about when we were going to leave for today's presentation, and I said, how about 8 o'clock? And she says, well, by the time you get there, your talk will be over. And unfortunately, my geography of the state is still not very good, as I thought Sanabel Island was off the coast of Jacksonville. So if it wasn't for Regina, I wouldn't be here today. So thank you very, very much. We're all very much aware of the extreme importance of landfills, and the purpose of this discussion is to talk about hydrogen sulfide and exactly what might be able to be done to mitigate this from a nuisance point of view and also from the potential health effects that can be materialized to those who are working around landfills and those who are living in near proximity. Within the landfill, there can be very high concentrations of hydrogen sulfide. Typically at the surface, we see much lower concentrations. For example, less than 10 parts per million, but as subsequent slides will show, even at 10 parts per million, this is a concentration that we should be very concerned about. When we look at the mass of a landfill, it presents another challenge. How can we best mitigate this particular constituent, hydrogen sulfide, when the land mass is in excess of acres? Much different situation in looking at, for example, water treatment, industrial water treatment, or many air pollution control systems that are point of source. We can look at, have an engineering solution because we have a certain flow of water through a pipe or a certain gas flow rate, and then design around that. Here, this is a much bigger, much more challenging topic. Certainly there has been many solutions, natural soils, quicklime, and what we were looking to do here was have something on the same magnitude with respect to cost, but that would be much, much more effective. If we look at landfills, we must wonder, well, where does this hydrogen sulfide initiate from? And sulfate, which is abundant in a variety of different materials, particularly, for example, in drywall, can be broken down by sulfate-reducing bacteria, and we have this hydrogen sulfide emittance. And for a ratio of about every 100 tons of sulfate, we would see that we would have roughly about 35 tons of hydrogen sulfide emitted. I think all of us are very familiar with that hydrogen sulfide. That's that rotten egg smell that we've all detected, at one point or another. So I talked a little bit about why are we concerned about hydrogen sulfide, and this particular graphic, I think, really puts forth the seriousness of the concern. We'll start towards the bottom, and we can see that high concentrations can cause death. If we go to those concentrations, which are typically at the surface of the landfill, say, for example, at less than 10 parts per million, we have nausea, we have headaches. And then at some intermediate concentrations, say for example 100, then there could be some throat irritation and still might be some loss of life. And so this is a particular constituent that is of concern within the landfill and those living in close proximity. Interestingly enough, if we look at what's been done across the US, there's not a lot of standards surrounding this particular constituent. We can see that California, Minnesota, Montana, et cetera, have put forth ambient air quality standards, and many of these are around a time sequence. So often when we think about quality, water quality, or air quality, it would be a certain concentration. Our drinking water standards suggest that we shouldn't have a certain milligrams per liter of, for example, benzene, but it doesn't necessarily point out that that's over a certain time period, for example, an hour or a day or a month or a year. But here we can see it's a much different situation where we're looking at the exposure within a certain period of time, and all of these concentrations are in parts per billion, and the previous slides that I was referring to are all talking about parts per million. In other words, the constituent hydrogen sulfide is present in much higher concentrations than these ambient air quality standards put forth by these various states. As John mentioned, I graduated from Penn State. I interviewed in February of 2000, and there was two reasons why I chose the University of Florida. One certainly was it was 80 degrees. I think it was snowing when I left Penn State. It was beautiful weather as I got to walk around the campus. The second reason, and actually probably the most important reason, was the university's affinity, their passion for commercialization of technologies. I wanted to get into commercialization day one. Didn't want to wait for this magic thing called tenure. I wanted to be able to have students engage in research that was meaningful to constituents that ideally went and solved problems, and we've been very successful in doing so. And what I really like about the Hinkley Center is the continuation of that concept of trying to take these ideas and get them into commercialization. And with this particular project, the concept of commercialization was at the get-go. And here are some schematics, some diagrams of what we refer to as geotreat mat. The concept basically is to take, for example, a geotextile membrane, something that's used in and around landfills on a regular basis, and then impregnate it with a certain material. And that material that was chosen is known as activated carbon. And to me, it's the best substance on the world. I learned about it as an undergrad, pursued my master's and Ph.D., and have been very fortunate to work with this material for a variety of different applications. You might be familiar with it in your Brita filter. It's used in aquariums. It's used in water treatment. It's even used in products like makeup. There's so many different applications for the material. What does present some challenges with it is that it can be expensive. So our objective here was to look at how can we make an inexpensive activated carbon, but unfortunately, activated carbon's capacity for hydrogen sulfide is very low. So what can we do to enhance its properties? I'll talk about that enhancement here a little bit, but the whole idea was to take this activated carbon, a low-cost sorbent, impregnate it with a particular catalyst, and then add this into this geotextile membrane, and as you can see in the cartoon, roll this mat out over the surface of the landfill as its various layers are being developed, and roughly looking at somewhere around a $2.50 per square foot cost, and that, based on the statistics and the variables that we were able to see, would represent a 20% cost savings compared to other solutions. So again, commercialization is really driving this concept from the beginning, and so therefore we looked at municipal landfills, construction debris landfills, and then also wanted to identify, well, what was our targeted area for the innovation? And you can see most of these categories are yes, new waste placement all the way down to inactive area that consists of a thin layer of soil are the concepts here that we would use this geotreat mat to be able to mitigate hydrogen sulfide and other odors as well. So what was the catalyst that we wanted to use? Well, we chose iron. And we chose iron because primarily it works very well for the removal of sulfur species. Many of us might be familiar with pyrite, and that would just be Fe as an iron S. And so we know that it can sorb sulfur very well, and it happens to be inexpensive. Ferric chloride, ferric sulfate are used abundantly in water treatment, and therefore they're relatively inexpensive, they're easy to transport, and what can we do to now get this material onto the surface of activated carbon, make this very high capacity sorbent? Again, hydrogen sulfide will react well with the iron oxide, particularly in the presence of humidity. And we wanted to target high capacity because we know that there's going to be other constituents that the activated carbon is going to want to absorb. And that's okay, because the activated carbon here is almost to an extent serving as a base for the iron precipitate or the iron oxide. Some of the carbon will remove the hydrogen sulfide, but really what we're looking for here is for the iron to do the majority of the work. Then we wanted to look at two ways of implanting the iron onto the activated carbon surface. Chemical precipitation is one that's relatively simple and straightforward. In the laboratory, it's extremely easy. In fact, a lot of research is really easy in the laboratory. How do we transfer this to manufacturing? And there, that presents an interesting challenge. When activated carbon is manufactured, we start with a highly carbonaceous material, wood, coconut, coal, for example. We heat it up to high temperatures, roughly 850 degrees Celsius. We expose it to steam, and this steam creates a lot of holes or pores in the activated carbon, and that's why it works so well. When the activated carbon cools, we can do so what we call by steam quenching. If we don't quench the carbon, it becomes extremely reactive and actually somewhat dangerous. So the thought here was, as the carbon cools, we can hit it with steam, but also have with this steam some of these iron salts. The water would flash off, leaving the iron on the carbon, and therefore we saw this as a way of going from the concept right to commercialization in a shorter period of time. So what were we looking at here with the overall context? One of my goals as a professor is not necessarily to come up with Mazyck's equation. I wasn't really interested in doing that because most people can't pronounce my last name. It's Mazyck, it's Mazyck, so they'll never get the equation right, so I threw that out the door. Our dean would like to see the number of dollars that we bring in on a yearly basis. Okay, that's a good metric. But what I really wanted to do when I turned 70 is just stop for 1 second and think about how many US high technical jobs have I been able to create. That's been my mission. That's why I chose to be a professor. That's why I chose the University of Florida. And on that momentous day, 50, 60 years from now, because I'm nowhere near 70 yet, I just want to stop and think, was I able to create a lot of jobs? And so part of this is also about doing so. Activated carbon is produced, for example, here in the state of Florida, roughly about 3 hours north from here. I do have that geography correct now that I know where I am. Marketing, manufacturing, consulting, et cetera, are all potential areas of growth for this type of technology, generates revenue, and then certainly the quality of life. That's really what we are doing in environmental engineering. We're very strongly connected to two components, the environment as well as public health, and it's provided a tremendous opportunity for students to gain hands-on practical research, and then they can use those experiences to go on and get a job. Rachel, for example, completed her master's degree in this project. She's now employed, and that's always very exciting to see your students be able to get jobs after their work. We had 3 objectives. We wanted to first verify that we could impregnate or add the iron onto the activated carbon, and then also indicate that indeed this was going to work well for hydrogen sulfide removal. Within this, again keeping commercialization in mind, was could we do this inexpensively? Would we be able to use this steam quenching approach versus the precipitation approach, knowing that the precipitation approach is going to add costs and therefore potentially prevent the technology from making it to market? And then the final objective of this particular work will be to create a prototype. For 10 years, I was fortunate enough to work with NASA, where we developed a lot of different prototypes. And what we learned in that work, as we took those ideas that were effective for space station and we wanted to get them commercialized for terrestrial applications, is that a prototype was worth 1,000 words. Being able to take something to the potential user or to the manufacturer, show them what you've done, tends to get them more excited and shows that you've really thought through the idea. So here, as we wrap up the project in a couple of months, we'll look to create that prototype of the GeoTreat mat. A little bit of cartoon here on the right side, and this is how we are going to assess the effectiveness of the carbon for hydrogen sulfide removal. So if you have a hydrogen sulfide cylinder, we just purchased that commercially through air gas, and we're going to control that through some mass flow controllers. And then we'll go through our sorbent bed. We have an analyzer that we can basically look at the concentration before the sorbent bed and then the concentration after the sorbent bed. And we are going to look at a variety of different iron oxide species, ferric, 3+ ferrous, 2+, to create Fe3O4 or magnetite. And we wanted to look at this in various ratios. How much carbon to iron did we want to have? If we add too much iron, then we might just block all of the pores of the activated carbon, and that's necessarily not going to work well. We would like to get the majority of the iron down in the pores, because one of the concerns is we don't want this material to leach. We don't want to solve the hydrogen sulfide problem, but then all of a sudden introduce all this iron into the landfill. Again, we look at the gas phase sorption, and we'll look at some data here in a little bit. The core of my research over the past 17 years has been in activated carbon manufacturing, engineering it for a variety of different applications. And so this particular furnace is one that we've had in our lab now for quite some time. And basically what we do is we take our water, we create steam, and then we go through this temperature controlled regime where we're taking the raw material from roughly 650 degrees Celsius to 850 degrees Celsius. We're turning these raw materials that have almost no surface area into a high surface area material, and we create activated carbon. Well, as that material is cooling, the concept is that we would then take a solution of our iron species and then inject that onto the carbon while it's cooling, and then ideally get the iron implanted, and then we could therefore accomplish this steam quenching in these various ratios. And as I talked about, eventually then we'll look to probably do something around a 6x6 inch square of the GeoTreat mat, and we've been targeting somewhere between 0.5 kilograms of iron activated carbon per meter squared. And then eventually that mat will also be tested. And we're working at higher concentrations than what we would see at the surface of the landfill, and that's primarily just to accelerate data collection. We think the sorbent's going to work so well that if we used 1 to 10 parts per million, we'd get a data point once a month. That doesn't really work well for students who are trying to get out the door in a shorter period of time. It used to be that a master's degree was 2 to 2.5 years. Now they want to be out in 12 months. So they like to accelerate the data as quickly as possible. As we looked at this, we did say, well, what else is out there? And there is some proof of concept that iron sponges are working well for hydrogen sulfide technologies. There's also some scavenger technologies. We certainly didn't want to ignore what was already commercially available, and we thought about those, and then we incorporated them into, here's some activated carbon that has been impregnated with or precipitated with the iron. We know that pretty well because we can see the color has changed. Many of us are familiar with iron, has that rusty color. Activated carbon is pitch black. So we can see that the two of them are making this brownish material. Again, inexpensive. The carbon has a large surface area, and what we want to do is take these iron species, have them react with hydrogen sulfide to form these very stable pyritic species onto the activated carbon. Now, we chose bituminous coal as a raw material for a variety of different reasons. One, it's relatively inexpensive, and it can be easily turned into activated carbon. So here's our coal source, and you can see that it really has no surface area. If we took this lump of coal and we put it into water that had like a blue dye in it, we'd have a glass of water with blue dye and a lump of coal. It wouldn't do anything. But if we took this activated carbon and put it into that food coloring into the water, it would remove all of that color. And that's why activated carbon is so well suited for things like water treatment. So we produced an activated carbon with roughly about 400 meters squared per gram. We're particularly interested in the size of the pores because we do want to try to get some of the iron down in the pores, so we need big enough pores for the iron to fit. And we track, for example, how much microporosity is going to be available for the overall surface reaction, and then 100% just driven by commercialization is how much mass loss. So this basically means that we started with 1 pound of coal and we ended up with 0.53 pounds of final product. Now that may seem like a lot of mass loss, and it is, but traditionally when activated carbon is produced, there's at least 80% mass loss. So again, trying to think about the economics of the project, we wanted to create a suitable material, but not yet have so much of it lost in the manufacturing process. So here we have our precipitation. That was the first way, proof of concept. We started with ferric chloride and ferrous sulfate, both of these readily available, commercially easy to transport from one location to another. And what we were going to do is that these are stable at low pH, so we wanted to cause a precipitation reaction, so we would add a base. And we chose 10 molar of sodium hydroxide, and then we would create these various ratios, and we'll talk about how those worked here in a little bit. After the material is produced, we dried it at 110 degrees just to drive off the moisture. And here again, perhaps you can see why we wanted to use that steam quenching approach. To take activated carbon, put it into solution, and then dry it. That just uses energy, it takes additional resources, and prevents the technology from making to market. So here we can see the iron salts in DI water, and here they are with the activated carbon to make the activated carbon iron precipitate. I won't go through all of these in great detail. Very briefly, we have the sample name, the ratio of carbon to iron, the total surface area, the size of the pores, the total volume of pores, and again, this microporosity that we wanted to keep an eye on. And I think what was interesting here is that there wasn't a significant difference in the surface area between the 50:1 and the 5:1. We're certainly losing some surface area, and again, this is the iron filling these pores, and that makes sense. But we haven't drastically reduced it. In other words, we haven't gone from 400 down to 10. We still have a lot of surface area available to ideally participate in some reactions. Now, universities are pretty neat because they got a lot of very expensive instruments or tools that we can do things with, and these instruments improve with time, allowing us to further understand our materials. So energy dispersive X-ray spectroscopy is one way of looking at the elements on a given surface. And over here, we just have the activated carbon, and we can see a variety of different elements, and I apologize for the small print, but what I want to point out is there's not really a lot of native iron on this particular material. But as we see in the 50:1, for example, 5:1, we start to see these peaks of iron, and that's basically indicating to us that indeed the iron is getting on the carbon, and we can use this as a verification tool. We don't necessarily be able to compare the magnitude on the y-axis, but it does give us a relative indication that indeed we are getting at least 2 species of iron on the carbon, and that's what we expected. We then move on to some microscopy pictures, and we've got this relatively rough surface of the activated carbon. Perhaps looks like the moon, for example, and we can see some smoothing out of that with the variety of different iron precipitated materials. And again, this is just reaffirmation that we are getting the carbon on and into the pores, and what we're trying to really understand here as well is how big are these? And so we'll look at the scale. Here we've got roughly a 10 micron scale. Are these 1 micron, are they 5 micron, are they 10 microns? As we can reduce the surface area, as we can reduce the particle size of these iron agglomerates, we can increase their overall effective surface area. And the next phase of this research, we'll be looking at doing that. Partly what we want to do, when we created these through iron precipitation, we used 110 degrees. We want to increase that temperature in subsequent experiments, and partly we'll be able to sinter that iron. We'll be able to shrink down some of those particle sizes, and we think that's going to even further improve the performance. And then we also just wanted to know the overall pH of the materials, and regardless of what iron ratio we use, and we see they're all about the same pH, albeit they are much more acidic than the activated carbon itself, but the good news is that they're all very close to still being neutral. So here's our Mazyck test stand. This is the schematic that I showed earlier, and here's what it looks like in real life if you were to travel up to Gainesville into Black Hall. We have our analyzer and mass flow controllers. We have our sorbent bed. We're going to look at some target concentrations. Again, to kind of accelerate the results, we are looking at much higher concentrations, between 100 and 500 parts per million. We had to vary the mass and the gas flow rate to try to get a really nice breakthrough curve. And let's look at some of these breakthrough curves. Okay, so on the y-axis we have the hydrogen sulfide concentration, and it's normalized C versus C naught. And then on the x-axis we have the length of time that the experiment was running. And if we look at these particular curves, well, we don't really see a lot of separation. They look like they're all performing about the same, whether we use 50 to 1, 5 to 1, or even the untreated. And I think that's really a manifestation that we're overwhelming the carbon with 500 ppm of hydrogen sulfide. But the curves tell us one thing. It is good to use some of that calculus that we typically learn in the first or second year and do some integration work. So we can integrate the amount of hydrogen sulfide that has been removed, and we can see that indeed that these iron-treated carbons do have a higher capacity, 600 versus 500. This one perhaps did not, but we have almost now here 800 micrograms of hydrogen sulfide, so we're getting significantly more performance compared to the virgin material, and that's a pretty exciting result. That verifies our proof of concept, and we believe that that's just the tip of the iceberg, that we're going to be able to double, if not triple. In fact, Regina's scheduled to defend her Ph.D. in March, and the deal is if she doesn't quadruple it, she's going to stay an extra year. Okay, 6 months since I thought Sanabel Island was by Jacksonville. And here we have some of the data at 100 ppm, and we can see here we're getting some higher capacities. So the 5 to 1 ratio was working significantly more than the 50 to 1. And again, proof of concept that we are getting the reaction that we wanted, and therefore very encouraging results. So where are we going to go from here with respect to the experiments? Well, the first is going to be to add some temperature. We're taking the iron precipitated carbon and we're driving it up to 110 degrees so that we can just remove the moisture. Next, what we want to do is bring it up to, say, for example, 300 degrees Celsius for a couple of reasons. One is we want to sinter this iron to create more overall surface area of that species. But equally important, we want to start to manifest a change in the crystallinity. So this iron on the surface, through those through the SEM images and through known iron chemistry, is very amorphous. We can kind of think of it as a sponge. We want more crystalline material. But that crystalline material is going to have more catalytic behavior, and as we bring the temperature up, we can go from the amorphous iron through what we know as goethite, and then into maghemite and into magnetite, and therefore, I think as we bring that temperature up to about 300 degrees Celsius, Regina will be able to defend her work in March and on time. We know that moisture is going to help the system. Right now, we've been doing all this dry. We've been trying to hinder our success. We realize there's going to be a lot of moisture available in the landfill environment, so we'll add that to also simulate the realistic environment. Just a little bit about the timeline, 12-month project, and we're making pretty good progress. And I won't spend much time on the deliverables. We do have a project website, but I did want to share some of the feedback. Another aspect of the Hinkley Center that I really like is the concept of this technical awareness group and getting the real feedback, from those who are true experts. And I'd like to point out a number here who have been very helpful in this process. And we walk through a subset of these slides and really put forward some great suggestions that we're thinking more about. One is in this geotextile mat. Yep, it's going to be exposed to UV, and therefore is there going to be some degradation. So that's one thing that we are considering how we can best deal with that going forward. As I mentioned earlier, the concept of no iron dissolution. Fantastic. You've solved the hydrogen sulfide issue, but now you've put 10 tons of iron into our landfill. Yeah, no, that's not going to be acceptable. So we'll do some verification that we aren't seeing iron dissolution. And then we know there's going to be competitive adsorption effects. We know that there's going to be hundreds, if not thousands, of other inorganic, organic vapors that the carbon's going to absorb, and therefore we'll give some of that some consideration. And we can do some of that through modeling efforts, as there are a number of equations that we can look at some concentrations of constituents and predict what's going to happen next. We told John and the board that we'd look at some other ways of funding the project afterwards, and I wanted to say that we have had a discussion with an activated carbon manufacturer. One of the things we'll be looking at is submitting a grant later in the year to the National Science Foundation, and where we're going to try to take the work in subsequent years is try to add some more sophistication to the technology, which is to be able to provide some level of indication to those who are going to deploy the mats, its effectiveness or its remaining life. So in other words, there's a sorbent there in this geotextile mat, but how do you know if it's got another month, another year, or another 3 years? So that's one of the aspects that we want to bring into the project. Regina presented the work recently at a conference up in Pittsburgh that was really well received, and here we are today. My first time in front of this audience. I thank you for welcoming us. It has been an absolutely fantastic experience, and without a shadow of a doubt, very thankful to the Hinkley Center for providing this opportunity. And if there's still time, I'd be more than happy to take any questions. John?
How did you come up with this idea?
Well, I was fortunate enough to be introduced to activated carbon at a relatively early stage in my career, and so that aspect of it and how it could work, I think, was kind of obvious. What we like to do with activated carbons is try to enhance them to make them better for a variety of different applications, and so we've been looking at different ways of catalyzing them and adding different constituents. And one of the really neat things about science is that nature teaches us a lot that we need to know. And we shouldn't ignore what's happening naturally. And typically when sulfur is prevalent in nature, it's there as pyrite, as FES. And so I said, well, let's not defy what nature's doing on its own. And we looked at some of the literature, and therefore, yeah, it proved to be a good first step. Iron can be as a catalyst in other reactions, and so we drove forward that concept, and it seems to be working really well.
Could you put something in the mat to show that when you have breakthrough, when you do stuff all prepared?
Yeah, I think that there's a number of ideas that we're thinking about to show some type of level of performance, and whether there might be, for example, some color indication. That would be ideal, to be able just to look at the mat and see that, yeah, there's some indication of a color change, and therefore, yeah, the mat is, we'd have to do some modeling ahead of time, but it's got, 3 months, 6 months, or, another year. There'll be some other biosensor type things that we can do as well, a bit more sophisticated, and yeah, I think we'll consider both of those and try to look see if we can convince NSF that those are good ideas to continue the work.
I think I could be loud enough. Okay. I know you're talking a little bit about the design of that, but I'm wondering if you have any plans for how to replenish this material after it's exhausted from the contaminants that it's absorbing.
Yeah, sometimes I prefer to work with organic contaminants because we can always break those down to CO2 and water and self-regenerate and get the material to, quote, last forever. With inorganic materials, yeah, it becomes much more challenging. We haven't thought at length about how best to accomplish that. Typically, if we have inorganic accumulation and we do want to reuse the material, then we would look at some type of water process where we might be able to remove those constituents. I think here more the concept was it's going to be relatively inexpensive, and it becomes almost a part of that, that permanent cap for the landfill, or at least that temporary as they're working. We put that down, perhaps put some soil on top because of this UV degradation issue that has been brought up. But instead of looking at it as rejuvenation or regeneration, it's essentially a one-time life. So what can we do to make that lifetime as long as possible?
During your presentation, you talked about the effects of sulfide on health and the environment, but I also understand that sulfide has an effect on the biogas that's used in turbines. Would your technology be looking to increase the quality of biogas?
Yes, absolutely. Yes.
And you said you have a website with the research?
Yes. Yes, John, how will we best provide the website for the...
People can link to it through our Hinkley Center page, or if they usually typically, if you Google the professor's name and some words from the project, they're right on the website. And all these videotaping, all this is all going to be on our website. Sorry.
And what we'll do with SWANA Florida is we'll go ahead and put that up on our website as well. We'll put a link to the Hinkley Center on there.
Great.
Dr. Mazyck, with the granulated activated carbon, once you impregnate it with the iron, do you see a reduced permeability of that carbon, or will you still have good hydraulic conductivity through the material?
Yeah, no, still excellent hydraulic, conductivity properties. I keep seeing these hands. I get nervous. There's a number of former students out there. I'm wondering if they're trying to get revenge. This is their time. So so far I'm dodging the bullets. I see the big smiles on their face. I'm just waiting.
You may have already covered this, and I may just have missed it, but you were talking about the steam quenching technique and the chemical precipitation technique, right, for getting the iron on.
Yes.
Which one did you use in the testing that you done so far? I wasn't quite sure.
Yeah, everything that has been done thus far has been through the iron precipitation technique. Yeah, we're moving on to the steam quenching,
You
right?
haven't experimented with that yet, but
No.
it's gonna work or not.
Yeah, correct. We're optimistic. I think that we're going to struggle to be able to get the nice uniformity on the carbon that we do in the precipitation, technique, just the way the bed's going to work. But if we can at least show proof of concept, then I think there's engineering ways of controlling, that uniformity. But we feel pretty positive that as we move into that, we'll be able to accomplish success.
Thinking into the future and obviously the commercialization of the product, landfill operator having an issue with H2S. How do you envision selling that to the operator and kind of the phases of, installation, during operation, and, both cost versus the alternative, and also, this looks like a surface, obviously treatment for that H2S. A lot of it is going to be from the gas collection, so it's kind of that mix. But how do you sell it to an operator and go through the benefits of that product?
Yeah. Previous experience with commercializing technologies in different arenas, I found consulting firms to be very valuable. They have established these excellent relationships. There's a high level of trust and an in-depth knowledge of the particular issues, already. So I would envision consulting firms playing a very important role in working with the stakeholders to help, demonstrate, the benefits. Certainly the technological aspects also need to be equally, represented. So if we're fortunate enough to have a carbon manufacturer commercialize it, or for example, somebody who specializes in membranes, the mat, it could be either or, it could be a combination of those two, participating and talking about, the data, the technological aspects that got into it, and then, transparency on the, on the costs. When we put the proposal together, and we talked a little bit about here, we have gone through a pretty significant cost model in comparing what this would cost compared to the other solutions. We feel like we were, fairly thorough in that. And probably 3 or 4 pages of cost comparisons, and bring those forward as well, and try to have this holistic view from the consulting firm, the manufacturer, as well as the research side, to introduce that to the stakeholders. One of the things we'd like to do as we finish the project is have a potential for an audience beyond the TAG advisory board, but what we refer to as a kind of a hot topic hour. Try to make those in this audience and your constituents aware that, for example, we could do a teleconference, talk about the technology and the approach, and just start to introduce it. Typically it doesn't take hold, right away. There is this time, this patience in walking through it. Somebody has to be the purchaser of 001 serial number. That's not always easy, but if we can find that person, I think we can work this forward.
Anyone else?
Great, thank you very, very much.